Hello my scholars, welcome to my school YouTube channel. My name is Emmanuel. In today's video, we'll be looking at JAMB CBT past question chemistry in year 2024. Please don't go anywhere, stick around and we'll be right back. Welcome back to my school YouTube channel. Like I said earlier on, today we'll be looking at JAMB CBT past question in chemistry for year 2024. And in today's video, we'll be considering question 26 to 50. Now let's go to question number 26. How many moles of CO2 are produced when ethanol is burnt with 6 grams of oxygen? When ethanol is burnt with, so that means the reaction is actually between ethanol and oxygen, okay, to produce CO2. So we want to determine how many moles of CO2 will be produced. So you can do this without writing a balanced chemical equation first. So let's move on to the board so we can see what happens there. The reaction is actually between ethanol C2H5OH reacting with oxygen, okay, to give us CO2, okay, plus H2O. That's water. Okay, so we can balance the equation. We have 2 moles of carbon here, so here can be 2. So this is balanced. Oxygen is 4 plus that, so we have 3 here. So this is 6 plus 1, that's 7. This is that's 4. Okay, so we have 3 here. Okay, that's balanced now, I think. We have 3 here plus 4 here. Oxygen is balanced, and that is balanced. So which means that the reaction is actually saying, it says how many moles of CO2 are produced when ethanol is burnt with 6 grams of oxygen. We are given the mass of oxygen, okay? So that means we are going to compare the number of moles of oxygen, okay, to the number of moles of the CO2, the unknown that we want to find, because we want to find how many moles of CO2 is formed there. So first, stoichiometrically, this is ratio 1, okay, is to 3, is to 2, and then is to 3. But our emphasis will be on oxygen and CO2. We are given this known, and this is the unknown. So this is like 3 moles of oxygen will produce 2 moles of CO2, okay? So if 3 moles of this is what happens in the balanced equation. So it is expected that ideally 3 moles of oxygen will react with ethanol to produce 2 moles of CO2, okay? But in this case now, we're told that what happens if 6 grams from the question of oxygen reacts with this? How many moles of this will be formed? So we can just do a simple ratio. So first we need to find the number of moles of that 6 grams of this. So don't forget that number of moles is equal to mass over molar mass, okay? So we are given already that the mass of oxygen that we produce is what? 6 grams. Okay, so we can say that 6 grams over the molar mass of oxygen. Of course, oxygen is 16, okay, because it is a diatomic gas, so O2. So that means we will not just have 16 because we are finding this will be 16 times 2, okay, so that's 32. So the molar mass of oxygen gas will be what? 32. So 6 divided by 32, we're going to have 0.1875 moles, okay? 1875 moles. If we divide this by this, we have this. So now, don't forget that the ratio is between oxygen and CO2. So ratio 3 mole gives us 2 moles. Then 0.1875 moles will give us what? X moles, okay? So we can just do a simple proportion. If 3 moles, okay, of oxygen actually produces 2 moles of CO2, yeah, then 0.1875 moles of oxygen will give us what? X number of moles of CO2, okay? So if you cross multiply, you're going to have X will be equal to 2 times 0.1875 divided by 3. Okay, by the time you punch this on your calculator, you're going to have 0.125 moles. Okay, you can check it out. So 0.125 moles. So let's move on to the screen and see what we have there. So that is option A, 0.125 moles. So that is the number of moles of CO2 that will be produced when 6 grams of oxygen is burnt in ethanol. So the correct answer is option A. Question number 27. Which of these is the most preferred separation technique for the isolation of solutes where the purity of the constituent is of utmost importance? Where the purity is of utmost importance. Don't forget, like one of our video lessons, we talked about separation techniques. Okay, we said that mixtures are impure. Okay, so they have to be what? Separated, because different components or different compounds actually make up a mixture, okay, in physical process. Okay, so there's need for us to what? To separate in isolation, but we are looking at what? We are considering what now? We are considering the purity of that particular substance. So if we are considering purity, there are two things here. We have option A says sieving. Okay, sieving we only separate based on the particle sizes, different sizes of the mixture, okay, that make up. We want to separate them into different components. You have mixing, purity is not in place there. Distillation, yes. In fact, distillation is the process that is used in the breweries, okay, like we have Nigerian breweries, we have the spirited, drinks, okay, where they are manufactured. This process is used. What happens there? The mixture will be boiled, it will be applied. As it's boiling, vapor will be going off. As the vapor is being, it will be collected. The vapor will be collected into a pail, and then once it is collected, it will be cooled. As it's cooling, it will be turning back the vapor, that's the gaseous substance, will be turning back into liquid. Okay, so once that happens, you can get that. Of course, what you're going to have, you have it as a pure substance. Okay, for this, that's why you see that those spirited, this ethanol that are produced, they are in purity. You see their purity can have 99% and so on and so forth in the raw state, the concentrated state. So recrystallization is another process that has to do with eating also. The solute already, that's the salt, is already dissolved in the solution. So as we apply it, what happened? The solvent will what? We vaporize, okay, and leave the solvent and leave the solute, that's the salt, and leave it behind. Okay, when you have that, it is recrystallized, it is heated again, so that will give you a pure substance. In fact, when we are talking about the isolation of solutes where the purity is of the constituent is of utmost. So all the component of the mixture will be gotten at very pure. In fact, the high purity level of purity is very great. So for this, so we have this purity for this. Then precipitation. We only bring out the salt as you apply it, or you bring in maybe a solvent into it. What happens? You will have it precipitating out into solid phase, but that does not show the purity. The impurity is still there. So the two options now, if we eliminate with our elimination method, option A will be off because this does not determine purity. Then precipitation will also be off. We eliminated option A and D. So we have option B and option C. So both of them impurity. Now, when you look at both of them, in the level of purity, okay, it has been shown that distillation has about 99% purity of the substance that is being separated, okay, while we have recrystallization having about 99.9%, okay, of high level of purity. In fact, in the pharmaceutical industries, they use these methods. Okay, so both of them will definitely help us to attain the purity in the component that is being isolated, okay, that we want to actually separate. But when you compare the two of them, distillation is about 99% high purity, while recrystallization is about 99.9%. So you can guess what the answer is. So both of them are correct, but when you want to choose for the sake of this question, because this one is more accurate, okay, more than this, of course, the value of this is about 99.9%, this is about 99%. So our correct answer that we are going for here is option C, recrystallization. Now let's move on to question number 28. Okay, we have a graph here. You can see we have energy is plotted against reaction pathway, okay, and then we have reactants here on this side, and then we have a peak up here, then moving this way, and then we have this. Of course, this is where we have our product here, because you can see delta H change in enthalpy between here and here. So the question says, in the graph above, y represents what? Where is y? Y is this. So the distance between this hump, okay, and this reactant, energy of the reactant. Okay, that's what they want us to find. Of course, this should be a bonus mark. Okay, so let's look at the options we have. Option A says endothermic reaction. Is this an endothermic reaction? Endothermic reaction is a reaction where delta H, okay, is actually positive. What do we mean? It means that the change in the heat of products, okay, is higher or greater than the change in heat of the reactant. So if you subtract them, that means delta H for this is equal to delta H of product minus delta H of reactant. So if you subtract, you are going to have a positive value. But if you look at this now, okay, we have reactants here and then we have the product here. So if you trace this, let's say here is 2, you can assume here to be 2, while here is 4, okay? So 2, 4. So if you are saying delta H for endothermic, that means it must be positive. But in this case now, change in product, which is 2, minus change in it. So 2 minus 4, you are going to get minus 4. Okay? So that is minus. So 2 minus 4, you are going to get minus 2. So which is what? A negative value for what? Endothermic. So this is not endothermic reaction. Activation energy, exothermic reaction. There's no point bothering ourselves over endothermic and exothermic. Why? The reason being that is only showing what delta H is. But our emphasis is actually on what? On Y. So let's just move on to this. So activation energy, what is it? Activation energy is the amount of energy that is needed for a chemical reaction to take place, to occur, okay, for the reaction to keep going. The minimum amount of energy that is required for that reaction to take place is what we refer to as activation energy. And what is this? In a curve, in a graph like this, it is the distance or the difference between the energy of the reactants and the peak of the what? Of the bump, which is here. This is the peak of the bump here, okay, of the hump here, and then we have, this is the heat of what? The energy of the what? Of the reactant at this point. So the distance or difference between the reactant energy and then the peak of the hump is what we call activation energy, which is why. So that leaves us with no option than to go for option B is the correct answer, activation energy. Now question number 29. The ions responsible for permanent hardness in water are sulfates of what? This is another bonus mark, okay? Sulfates of what? Don't forget that hardness of water, water is said to be hard if it does not form lather with soap. When you wash some of your clothes with soap, you discover that it doesn't foam, it doesn't form lather, okay? It's just as if you are just wasting soap, okay? That is hard water, okay? We have soft water too. So what is responsible for that? We have two types of what? Hardness. We have temporary hardness and permanent hardness. For temporary hardness, just boil the water, the hardness is gone. You just find those come around the what? The kettle or the pot you use in what? In boiling. But for permanent hardness, you cannot remove by what? By boiling, because of the what? Presence of the sulfates of calcium salts and then magnesium salts. In other words, calcium sulfate, tetraoxosulfate 6, and magnesium tetraoxosulfate 6 is what is responsible, and salts of chlorides, okay, are what is responsible for what? For the permanent hardness, okay? So that is why we have, if you look at these options, we have Fe3 plus magnesium. This is correct, but Fe3 is not. We have calcium 2+ ion and magnesium ion. That is correct, okay, because it is calcium sulfate and magnesium sulfate salt that actually responsible for permanent hardness. We have this and this. This is not correct. We have this and this is correct, but this is not. So this is not. So the correct answer here is option B, calcium ion and magnesium ion. Question 30. One of the following is not a water pollutant. One of the following is not a water pollutant. Water pollutants usually will be chemicals, okay, that will harm the aquatic organism that live in there. We look at option A, says inorganic fertilizers, okay, that those are chemicals. If you get in, they make the water, okay, toxic for the aquatic organisms that are there, and then most of them begin to die. In fact, we have lead poisoning even getting into them, okay. When someone eats the fish, you begin to have option B, says warm water affluents, okay. Some of the water that are effluent, that are rejected from maybe from company, from industries, they just allow them out and then they are just being drained into the water bodies, okay. They harm, because of the chemicals in there, they harm the aquatic organism. We have oxygen gas. In fact, oxygen gas can never be a water pollutant, because the animals that live in there, they need oxygen to actually survive. Okay, so without much ado, this is not a water product. We have biodegradable waste. We have those wastes that can be decomposed from organic substances. When they get in there, they cause harm, okay, to they are water pollutant because they cause harm to the organisms that live inside there. So option C, oxygen gas, because it is required. The organism there, they need oxygen to survive, okay, for respiration. That's why we have what we call BOD, COD, you know, time goes on. So the correct answer here, the one that is not a water pollutant, is option C, oxygen gas. Question number 31. We have copper 2 oxide here, CuO plus H2. Of course, this is solid substance. This is gaseous. To produce copper, and then we have H2O water, which is gaseous. Okay, this is not liquid water, this is steam, because this is gaseous. Okay, so in the equation above, the effect of increased pressure on the equilibrium position is that what happens here? Okay, first of all, when we talk about pressure, okay, the effect of pressure in a system in equilibrium, if what we are considering usually, because you know that pressure is felt by gases, okay, gases or fluid. Okay, maybe those are in liquid or solid form, but for the case of equilibrium position, what we'll be considering or be looking at will be just the gaseous substances alone. Okay, so solid here, pressure does not have effect on it. Okay, so we have gaseous here on the left hand side, that's the reactant, and then we have, this is solid, so we don't have any business with this. We are considering pressure. This is H2O, this is gaseous. So our business is with H2 that is gaseous, and then H2 that is gaseous. Now the next question is that how many moles of the reactants do we have on the left hand side? How many moles of the reactant do we have on the right hand side? First, is this reaction, is it balanced? We have 1 mole of copper here on the right hand side. On the left hand side, we have 1 mole of copper here, that's balanced. Oxygen is just 1 here. Oxygen is just 1 here, that's balanced. Hydrogen is 2, hydrogen is 2, so the equation is balanced. So how many moles of H2 do we have? This gaseous one, we have 1 mole on this side, on the left hand side. Then the gaseous one is also what? 1 mole on the right hand side. Visit our video lessons, okay, that we have had in previous class when we talk about chemical equilibrium. We dealt so much on this, okay, so we don't have time to begin to go through all of this. So what we do is that we said that the side that has the lesser number of of moles, whether it's in the left hand side or on the right hand side, will be favored by an increase in pressure. Okay, but if this, then the side that has a higher level of higher number of moles, okay, will be will be favored by a decrease in pressure, vice versa. So in this case now, we have the number of moles of what we have, hydrogen on the left hand side, is equal to the number of moles of the gaseous substance we have on the right hand side. So on that note, the equation is balanced. So increase the pressure, no effect. Decrease the pressure, no effect. So an increase in pressure will have no effect on this system at equilibrium. Option A says the equilibrium is shifted to the right, to the left. If the equilibrium is shifted to the left, we are saying the left will be what? Will be favored. So more of the reactants will be favored. No. The equilibrium, option B, is shifted to the right. If the equilibrium is shifted to the right, so you say more of this product will be formed. So which means that you are saying that the number of moles of the right hand side is actually lesser than what, but that is not the case. Option C says there is no effect. Yes, because the number of moles of the gaseous substance on the left hand side is equal to the number of moles of the gaseous substance on the right hand side. Don't forget, gaseous substance only when it comes to effect of what? Pressure in equilibrium. Option C say more of hydrogen gas is produced. No, because you are saying that this will be what? Will be favored. So the correct answer here is option C. There is no effect. Now let's move on to question number 32. What method is suitable for the separation of gases present in air? This is another separation technique question. What method is suitable for the separation of gases present in air? First, you must understand that air is a mixture of gases. At least you know that in your elementary science, okay? Air is a mixture of gases, and because it is a mixture, that means it is impure, okay? It is an impure substance, so it is not pure. So because it is not pure, we have to separate it. And because air also is a mixture of gases, and those gases have their different boiling points, okay? So, and because of the differences in the boiling point, we know that the best method to use here is not just, of course, not catalytic cracking. We know that we have a big hydrocarbon that we are splitting. This is a mixture of gases. So we have fractional distillation here of liquid air, of course, more likely. We have thermal decomposition of air. If you decompose the air thermally, what happens? Most of them will be given up. There are some that support burning, they will go off. Some do not support burning, so you can use that to get the different gases into their different components. Okay, we have catalytic decomposition of air. That will not be using the catalyst to decompose it, it will not work. So the correct answer here is fractional distillation of liquid air, because number one, you will need to liquefy the gas first. Now, liquefaction of the air will mean that the air will be turned into into a liquid air. Okay, how do you do that? All you need to do is just increase the pressure and then reduce the temperature. Then when you do that, the air would be liquefied. Okay, then secondly, you will now separate. Don't forget that in the mixture of air we have CO2 present, we have water vapor present. There is mixture of air, water vapor. Okay, so we can easily reduce the temperature as the temperature begins to go down below 0 degrees Celsius. What happens? You will separate your carbon dioxide and then the water vapor. The reason being that the carbon dioxide will turn into what we call dry ice. Okay, dry ice and then solid ice. They are not the same. Dry ice is carbon dioxide. Okay, the solid form of carbon dioxide or carbon dioxide is dry ice, while solid ice is the solid form of your water. Okay, of course, goes beyond the freezing point. Okay, so in that way you would have separated the carbon dioxide and then the water vapor that is present in that air. So the remaining components can be separated by now you can find that. So the correct answer here is option B, fractional distillation of liquid air. Now question number 33. The principle which states that no two electrons in the same orbitals of an atom have the same value for all the 4 quantum numbers is the one. Don't forget the 4 quantum number we have. Talk about the principle, talk about the azimuthal or subsidiary, talk about the magnetic, okay, and then talk about the spin. Those are the 4. So it's saying, this principle is saying that all there is no 2 electrons, okay, that can have the same value, the same orbitals in all the for the quantum numbers. The quantum number, all the 4 that we have, it is not possible for you to have 2 electrons that have the same values for all of them. Okay, that was actually brought about by Pauli. That's why we call it Pauli principle. Option A says Haber principle. Haber principle is talking about the feeling of electron. Okay, that it will first of all start with the lowest energy level. First will be filled with electrons before you go to the higher energy. Like we have 1s, 2s, 2p. Okay, so you cannot leave 1s and go to 2p. Okay, so you start with 1s first before going to 2p. That's what the Haber principle is talking about. Ohm's rule is talking about the principle where when you are trying to fill each of the orbitals, okay, that each of the orbitals will take a single electron first. Maybe orbital, let's say we have 2p, where we have 3 different ones there. So you can't fill a box with 2. You must first of all fill each of the boxes with 1, 1, 1, and then you come back to continue to fill that. So you can't fill them with 2. They must take a single electron first before you go to the other one. We have also discussed this under periodic table and properties in our video lesson. So for chemistry, you can visit there so that you can also have more knowledge about that. So that's what the Ohm's rule. So Pauli exclusion principle was the one that actually talked about that no 2 electrons, this is what we have here, in the same orbitals can have the same value or the same number for all the 4 quantum numbers. And then dilution principle has to talk about maybe the concentration of a solution, reducing the concentration, maybe trying to form more concentration different from what we have here. So it is not this. So the correct answer is option C, Pauli exclusion principle. Now we move on to question number 34. How much of 5 grams of radioactive elements whose half-life is 50 days remains after 200 days? In fact, please just go to our video lessons in chemistry. We have done all of this. Okay, radioactivity, we have treated, we solved so many examples on that. So if you have any difficulty, you can go to there and then to that point, and then you try to get what we have. So, but for the sake of this, we are going to do justice to this. Okay, so how much of 5 grams of radioactive elements whose half-life is 50 days remains after 200 days. After 200 days. So there are different methods you can use in solving this. Even if you check it in your physics, okay, you will still see this kind of question. So you can use, there are different ones that are used. Some will use n subscript t equals to n naught, then you have, you know, pi lambda and all of those, okay. But there's an easier question, you know, approach we can use that will make it easier. Let's move on to the board now so that we see. We're given how much of 5 grams, so which means the original mass. The original mass, okay, of the element is actually equal to 5 grams. We're given that, okay. So say how much of that element whose half-life is 50 days, okay. So that means half-life of 50 days. So we can have this half-life. Usually we use this T 1/2 to represent it, is equal to 50 days, okay. We have 50 days, and then remains after 200 days. So 200 days is going to be what we call the exposure time, okay. How long are you going to leave that element to decay, okay? How long does it take to leave it? So it's going to be, we're told, for 200 days, okay. But what are we actually asked to find? We're asked to find how much of that 5 grams. So which means that if this 5 gram begins to decay until it gets to what? 200 days, okay? How many are we going to have? What are we going to have left in this, from this 5 gram, okay, after 200 days? That's what the question is saying. So we are saying that residual mass, okay, question mark. So we can have that because we don't know it. So now the equation, the formula for finding this is residual mass. Like I said, this is an easier approach. Residual mass is equal to the original mass of the element, okay, that went under radioactivity, all over what? 2 raised to power n. I am sure this one is not very tough for you to remember. Residual mass, that's what we want to find, is equal to the original mass, the 5 gram we started with, all over 2 raised to power n. But this n is meaning that number of activities, okay, and that is actually equal to what we call exposure time, because you might not be given number of activity, okay. So you might need to find this exposure time, which we are given in the question, for how long is it going to stay before it begins to decompose, to that, all over. Of course, I'm going to have half-life. Okay, I'll have half-life. I've used this for half-life instead of writing this long half-life. So we have that. So that means we can find our n, because we are given the original mass from the question, but we don't know, this is a constant, but we don't know what n is. Okay, so we can find that as exposure time equals to half-life. So exposure time is already given as 200. That is going to stay for 200 days all over. And the half-life is what? Is 50. Okay. I think that's so easy. So 50 goes there, 1 here, that is 4. So this is 4. So the n is equal to 4. So we can go ahead now and substitute this by saying residual mass. What is going to remain after 200 days is going to be, original mass was given as 5 gram, okay, all over 2, of course, because this is what we are doing. 2 raised power n is what? N is 4. So 2 raised power 4. So we can have this as 5 all over 2 raised power 4 is 2 times 2 times 2 times 2. Okay, that's 16. So by the time you divide 5 by 16, 5 divided by 16, you'll be having 0. Okay, let's say we have 0.16 here, impossible. So we had 0. Okay, that would be 15. That would be 3. Okay, 48. Subtract that, you have 2 left. Okay, from that 2, you have that there. That will be 1. 16 can go in 21 times. So we have what again? We'll be having 2 left. Okay, yeah. So we have 2 left. Add that, we have 32. So that will be 312. And then we have 80. Eventually 8. Add 0 to it. So that will be 16. That's 5. Okay, so that's 0.3125 is going to be what is going to be left after 200 days that you subjected this has undergone radioactivity. After 200 days, okay, is going to be what? 0.3125. 0.3125. So you can make that to 2 decimal, because from the options they are all left in 2 decimal places, okay? So 2 decimal places, 1, 2. This is 2, 0, so that is 0.31 gram. So let's move on to the board, to the screen, and see what we just solved now if we have an answer there. We have a 2.50 gram, we have 1.25 gram, no, we have 0.63, we have 0.31 gram. So the correct answer here is option D, 0.31 gram. Do you know you can take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link below that takes you to the Myschool website. There, you'll be able to download the Myschool mobile app for your Androids and Myschool software for your laptops and computers. Please go ahead and start practicing. Now let's go to question number 35. The group 8 elements are the inert gases because they do what? Don't forget, group 8 elements are also referred to as the group O elements, okay? And why are they called group O elements? Because their outermost shell is completely filled of electrons. Like we have the helium, we have the neon, we have argon, okay? Those are examples of the group 8 or the group O elements. So they have completely filled, you know, electrons in the outermost shell. So their valence electron is completely filled. They are not looking for, that's why we call them inert gases, okay? They are unreactive. In most cases, they don't undergo chemical reaction in most cases, okay? So option A says have lone pair of electrons on their valence shells. No, they don't have lone pair because all the electrons are filled. Option B says all have completely filled valence shells. Yes, all their shells are completely, like we talked about helium, we talked about neon, we talked about argon, okay, and so on and so forth. So they have a completely filled valence electron. Option C says are all solids. No, they are gases actually. And then option D says are all polyatomic molecules. No, polyatomic molecules are molecules that have, you know, more than 5 together, okay? Helium is not a polyatomic molecule. They say all of them. Helium is not polyatomic. Neon is not polyatomic, okay? Argon is not polyatomic, so this is not correct. So the correct answer here is option B. They all have completely filled valence shells. I hope you enjoyed this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Question number 36. Na2X, okay, gives us, is dissociated into 2 moles of sodium ion, then plus X2 minus, okay? The question says the bond between sodium and X is likely to be what? We have covalent, we have dative, we have ionic, we have metallic. Number 1, it cannot be covalent because covalent bonding is a bond that is formed between molecules, okay, that are non-metals usually, okay? So we can have that, and that usually will entail the sharing of electrons, okay? But in this case now we have sodium here. This is a metal, so it cannot be covalent. So this one is eliminated. Option B says dative. Dative is a type of covalent bonding. We call it coordinate, okay, bonding. In that case, the 2 molecules that are reacting together, that are bonding together, okay, will share electrons. But the electron that is being shared is not donated by the 2 of them like we have in covalent, okay? It is only one participating atom or one particular molecule that will donate the 2 lone pair of electrons that will be shared. Again, if you click on the link below, you will go see our video lessons on this chemical bonding. We have also treated that before. So this also is not. We have ionic bonding. Ionic bonding is the same as your electrovalent bonding that takes place between what? Metal and non-metal, okay? Now we have transfer of electrons, not sharing now, of electrons from the metals usually to the what? To the non-metals. So we have a metal, we have a non-metal, okay? It's more likely to be this. Let's look at it again. We have Na, we have X. This is a metal, this is a non-metal. So for us to have Na2X, so it actually meant that initially these 2, before they bonded, was actually from this what? From this X, okay, why this X has 1. So if this X gave 2 to this, okay, and this is positively charged and this is 2 minus, so it's meaning that this would have definitely been a non-metal, okay? Yeah, because it's the one that received 2 electrons eventually from this sodium. Sodium is donating 2 electrons to it. That's why we have 2 what? 2 minus, and then it could be oxygen, okay, it could be sulfur, any other element in group 6, okay, because we have 2 electrons at this point in time. So this is a non-metal. So metal and non-metal, transfer of electrons to a non-metal is what we call ionic or electrovalent bonding. So this is correct. We have metallic bonding. This cannot be metallic because we have a negative charge here. So we can have metals are not negatively charged. Metals are positively charged. So option D is also eliminated. So the correct answer is option C, ionic bond. Question 37. The highest isotope of hydrogen is what? What are isotopes? Isotopes are usually two or more forms, okay, in which elements can exist. When we say two or more forms, elements that have, or atoms of the same element. Yes, let's put it that way. Isotopes are atoms of the same element having the same atomic number but different mass number. The mass number different, but the atomic number, and so they can be two, we can have three of them. In the case of hydrogen, we have about 3 isotopes. The first one is protium, okay. Protium has this H11, okay. Then the second one is deuterium. Deuterium has 2,1, okay, or some will write it as H21. And the third one is tritium. Tritium has 3,1, okay, or some will write it as H31. So usually these are the what? These are the isotopes of hydrogen. So, but this actually is the most common because it has 1 proton here. Okay, so this is most common among them, but we are talking about what? The highest isotope, of course, among the 3. This is 1, this is 2, this is 3. So you bear us witness that 3 is the highest, so which is tritium. So option A says deuterium, that is not correct. Protium, that is the first, and then tritium, okay, that is the third, and then positron is not it. So this is not it, this is not, this is eliminated. The correct answer is option C, tritium. Question number 38. When sulfur 4 oxide is passed into solution of acidified tetraoxomanganate 7, the color changes from what to what? Sulfur passed through what? Acidified tetraoxomanganate what 7. That's what we call KMNO4. So that reaction usually is a redox reaction. Okay, we have the KMNO4 acting as the oxidizing agent. Okay. While the SO4, which is SO2, which is sulfur 4 oxide, will be the what? The reducing agent in that point. So once that happens, don't forget that tetraoxomanganate 7 actually has a color that is purple. That is the color of KMNO4. Okay. So once it is introduced, it is passed over the sulfur 4 oxide, the color will change of the whole mixture will change from purple color to become colorless because it would have been oxidized. So option A says blue to green, no. Pink to yellow, no. Purple to colorless, yes. Orange to green, no. Because all of this, it cannot be A because the color of tetraoxomanganate 7 is not blue, it's not pink, it's not orange. So once you know the color of what? Tetraoxomanganate 7 is actually purple. So once it's passed over what? Sulfur 4 oxide is passed into this. What happens? The color will change from that purple it used to be. It becomes colorless because it has undergone reduction reaction. So the correct answer here is option C. Now let's move on to question number 39. Water gas obtained from the gasification of coke. Of course, your coke is your carbon, okay? Of coke is made up of what? This is another bonus mark, okay, for you to just. Water gas is also referred to as synthesis of gas. Synthesis gas, okay? Synthesis gas is just reaction of what? Of this coke, which is carbon now, reacting with steam, okay? When you react with steam, which is H2O, steam in gaseous form, you will end up having hydrogen, okay, plus carbon 2 oxide. Hydrogen plus carbon 2 oxide. So that is what we call water gas. H2 plus CO together like this, we refer to them as synthesis gas, or what we call water gas. So option A says nitrogen and carbon 2 oxide, but nitrogen, no. Option B, nitrogen and hydrogen, no. Option C, hydrogen and carbon 2 oxide, hydrogen and carbon 2 oxide, yes, that's your synthesis gas, or that's your water gas. And then option D is carbon 2 oxide and carbon 4 oxide, no. So the correct answer here, the water gas obtained from the gasification of coke is made up of hydrogen and carbon 2 oxide. The correct answer is option C. Now question number 40. Okay, sulfur 4 oxide can be used as a, there are questions that are just there for you as bonus marks, okay, so you don't waste time on them. Okay, sulfur 4 oxide can be used as a what? Usually it is used, in the olden days, sulfur 4 oxide was being used, as a refrigerant. It's basic, okay? They use it in preservative, okay, of your stuffs. You can keep them and then you can conserve them. Once you bring sulfur oxide closer to them, you can conserve and try to inhibit or try to hinder, the growth of microorganisms, okay, of that substance that you bring towards. So because of that, okay, sulfur oxide can be used as not a coating agent, okay, not a dehydrating agent, not a drying agent, okay, but what? A refrigerant, okay. So if you use it, you can't use it as drying agent because it does not have the power to drain, okay, moisture. Whatever thing you want to use as a drying agent or dehydrating agent should be able to remove the moisture of water. If you bring SO2 closer to water, it's going to react, okay. You have H2SO3 or H2SO4 as the case may be. So the correct answer is sulfur oxide can be used as a refrigerant. Option C is the correct answer. Question number 41. The molecular formula of a hydrocarbon with an empirical formula of CH3 and a molar mass of 30 is what? Of course, this should be also an easy question. So let's move over to the board and see what we have. Molecular formula is what we want to solve out. And then we're given the CH3. CH3 is the empirical formula. So don't forget that empirical formula, okay, empirical formula, okay, times N is equal to molecular mass, okay, molecular mass. So empirical formula was given as CH3. So we have CH3 here times N, we have it N here, equal to molecular mass was given to be 30. So we have 30 on this side. So don't forget that your carbon is equal to 12. That's the mass. Hydrogen is equal to 1. Okay. So this will be, we have C here. That will be 12 plus hydrogen is 1. But we have 3 of that. So times 3. Okay. All in bracket times N equal to 30. So this is 12 plus 1 times 3 is 3. Then we have N here equals to what? 30. So 12 plus 3 gives us 15. Then we have N here equal to 30. Of course, what do? Divide both sides by what? By 15. So that we have N. This cancels out this. So N will be equal to here is 2. Will be equal to 2. So we are not stopping there. This is the empirical formula, which is CH3. Okay? N. Now, we can substitute the value for our N here because we want to find the molecular what? Formula. Okay? So we have, this is written as CH3 in the bracket. Instead, in place of N, we got it to be 2. That will be 2. So that will be equal to, so we can use this 2 now to open up the bracket. This is 1 here, 1, this is C. 1 times 2 here, that is 2. Then H here, 3 times 2. Okay, we have it here, 3 times 2. So that will be C2H6. C2H6, of course, that is your what? That is your ethane and alkane family. Let's move on to the screen and see what we have. The molecular formula of hydrocarbon with an empirical formula. We have C2H4. This is ethane. No. We have C3H3. No, that is not. This is propane. Then we have C2H6. C2H6. Yes, that's what we have there. So the correct answer here is option C. Now, question number 42. The difference in molecular mass between an alkene and alkyne with 6 carbon per mole is what? Alkene and alkyne with 6 carbon per mole. So, which means an alkene family that has carbon 6. Let's go to the board. Okay, alkene with 6, alkyne with 6. So, which means that is C with 6 carbon. That will C6H. Then don't forget that alkene, usually they have CnH2n. That's their general formula, okay? So if N is 6 here, so H should be what? 2 times 6, okay? So that will be 12. So that is your alkene. While alkyne, okay, has the formula CnH2n minus 2, okay? So we have, so that will be C. Don't forget, both of them are carbon 6, carbon 6. So C6, so when N is 6, H will be this. 2 times 6 is 12. Minus 2, that gives us 10. So this is your alkyne. Okay, so the question says that the difference in the molecular mass between an alkene and alkyne with 6 carbon per mole is what? So you can go ahead and just say 2 times, this is of course 6 times, difference is the molecular masses. So this is 12. 12 times 6 plus 1 times 12. Okay, so this is 12 times 6 is 72 plus 1 times 12 is 12. So that gives us 84. Okay, then let's look at this. 12 times 6 is what? This is 12 times 6 plus 1 times 10. Okay, this gives us 72 plus what? 1 times 10 is 10. Okay, this is this 70, that's to be 82. So what is different between 84 and 82? That is water 2. Now, for the sake of exam, okay, this is just to explain what the difference is. To make it easier, because we are looking for the fastest way to solve your questions and get accurate answers. You don't need to go through all this route, okay? If you understand that, what's the difference between the homologous series? We have C6H12, C6H10, okay? C6H12 and C6H10. This and this are the same thing, okay? So we just have H12 here and then we have H10. So H12 minus H10 is what? That's H2. That's all. So you just say hydrogen is 1 times 2. So you just have to. So you don't need to waste time going through all this 12 times this, 12 times. Anyone that goes through this, you are going to spend more time than this. So just compare the two of them. Carbon 6 and carbon 6. So they are off. So we have H2 and H10. Take away this, we have hydrogen, 2 of that. So hydrogen is 1. 1 times 2, you just have 2. So let's move on to the screen. Option A says 10. Option B says 12. Option C says 2. Option D says 14. So the correct answer is option C. Now let's move on to question number 43. We have a table here. We have compound S, compound T, compound U, compound V, compound W. And then we're given the formulas of each of them. Compound S has RO, R prime. R prime is meaning that is an alkyl group, okay? So this could be CH3, while this is CH2, CH3, or C2H2, CH2, CH3, okay? Then we have RCOOH prime, this, and this, okay? Of course, this is for ether. This is for arachidonic acid. This is arachidonic. Okay, let's just move on. You say from the table above, which of these 2 compounds can form functional group isomers? Functional group isomers. When we talk about functional group isomers, we are talking about isomers. Don't forget that isomers have, isomers have the same structure. Okay, when it talks, we have the same molecular formula. Okay, but different structural formula. Different structural formula, the same molecular formula. That's what isomers are. They have different structural formula, but they have the same molecule. So the number of carbon is the same for the 2 of them or 3 of them. The number of hydrogen will be there. If you have oxygen, it will be the same thing for all of them. So which one among these compounds actually have the functional group of isomers that are the same? Though when you draw them, they might not have the same thing. So option A says S and T. S and T. S and T is ROR prime and RCOOH. Okay, no, this cannot be because if you have, let's say we have CH3 here and then we have CH2, CH3 here. Okay, because of this ether, this O that's here, you discover that the number of carbon definitely will be more here because we have R here, we have H here. Okay, and then we have C here. So the number of carbon cannot be the same. So this cannot be. So we eliminate this. Option B says T and U. T and U is this and this, this and this. T and U. So we have the number of R will be the same. Okay. The number of C will be the same. But because we have 2 oxygen here, we have 1 here. So they cannot be isomer because the number of oxygen definitely will be more than the number of oxygen in this place. So they are not isomers, functional group. So option B is eliminated also. Option C says S and V. S and V, we have S here, we have V here. So let's take example. If let's assume that this is for this ROR prime, and then we have ROH prime. Okay, so we have let's say we have CH3 here, oxygen here, then we have CH3 again. Okay, let's use CH3 for the 2. Then for here we have CH3 here. Okay, we have CH2 because this R can actually be, because we want to make the number of carbons to be 2. CH3, CH2, then we have O here, then we have H here. So let's see now. We have, how many carbons do we have here? 1, 2. So we have 2 carbon. How many hydrogen do we have here? This is 3 plus 3, that's 6. Then we have 1 oxygen. So this is the function of the structure of that. Then look at this. How many carbons do we have here? 1, 2, that is 2. How many hydrogen do we have here? This is 3 plus 2, 5 plus 1, that's 6. Then we have O here. So you can see that they are actually the same. So they are isomers. So we can say that option C is correct because S and V have the what? The same functional what? Group isomers. So they are functional group isomers. So because of that, option C is the correct answer. Now question number 44. Fats and oils are esters of fatty organic acids combined with a trihydric alkanol, commonly referred to as what? Trihydric alkanol. That means we have about 3 OH group that are attached to that carbon atom. So we have fatty acids or esters of fatty acids. When we talk about esters, esters are actually obtained from reaction between alkanoic acid and then alkanol. Okay, we have alkanol with alkanol. That's why we have ethanol reacting with ethanoic acid to form ethyl ethanoate, okay, which is your ester, okay, and then water. Okay, so in that kind of reaction, we have OH reacting with that. So for the sake of it, we have ethanol. Ethanol is not, because we talk about the fatty acids that are esters, okay? So ethanol cannot be a fatty acid, okay? The reason being that it is a general name for alkanol. It has this formula C2H5OH, okay, or CH3CH2OH, whichever way. So this is not an ester, it is just an alkanol, okay, it's just an alcohol, just ethanol, okay. We have this. So this is not ester. We have methanol. Methanol has CH3OH, okay. Of course, this is spirit. This is a spirited. Both of them are spirited alcohol. Okay, they are spirited. They can use them. They produce them as spirit as they are used in pharmaceutical company and but they are not esters. Okay, they are not esters. So we have glycol. Glycol is also not. Okay, glycol. We have CH3. We have CH2. We have OH, and then we have this as another form of alkanol. Okay, but we have glycerol. Glycerol is used usually, of course, when you are producing your soap, okay, what we call saponification, fatty acids reacting with alkali, okay, sodium hydroxide, to give what we have. Glycerol will be gotten as one of the products, okay, with the soap, okay. So that glycerol, which is usually we call it propan 1,2,3 triol. That's another name. That's the impact name for this trihydric, because we are saying we have 3. Propan 1,2,3 triol. So there are 3 OH group. This one has just one OH, but this one has about 3. Propan 1,2,3 that we will not draw it for sake of time. So we can just have the propan. We have about 3 carbon atoms, CH3, CH2 with OH attached, CH with OH attached, then CH2 with OH. So there are about 3 different. That's how we call it trihydric alkanol. So glycerol is the correct answer. So this is not. So the correct answer here is option D, glycerol. If you have any question bothering you at all, please feel free to ask. You can do that by just clicking on the link in the description below that takes you to the Myschool website. There you'll be able to ask whatever question that is bothering you, and solutions will be provided within the shortest period of time. Now let's go on to question number 45. Determine the half-life of a first order reaction with constant 4.5 times 10 raised to power minus 3 per second. Usually, if you look at the graph, in what we're discussing about radioactivity of elements, okay, or spontaneous reaction under our video lessons in chemistry, we talked about and we showed the different graphs that we can have for 0 order, for first order, for second order, okay. But for the sake of this, because of time, we just move on to this. So the formula for finding the first order for the first order reaction, okay, is we want to determine the half-life is this. Let's move on to the board now. So we say that half-life, okay, already we know now that this is half-life, okay, for the first order, okay, is actually equal to, we have a constant ln 2, okay, natural log all over lambda. Lambda is the constant, okay. So usually ln 2 is 0.693. If you check your calculator, you will confirm that ln 2 is 0.693. than that. So most textbooks, some textbooks will just find ln 2 over lambda. Some will just make use of 0.693 over lambda. This is your constant. So I think it's just so easy. We have 0.693 divided by, we're given what the constant is, which is 4.5 times 10 raised to power negative 3. Okay, so by the time you solve the 0.693 divided by 4 points, that we'll be having divide that with the calculator, we have 154 seconds. Okay, 154 seconds. So the half-life, okay, of a first order for the constant of 4.5 times 10 to the power minus 3 is actually 154 seconds. Let's move on to the screen now. Let's see. Option A has that 154 seconds there, 15.41540. So the correct answer is option A, 154 seconds. Do you have better explanation to some of the questions that we have solved so far? Please do well to share. You can do that by just going to the comment section, where you'll be able to indicate the question number and then the answer you wish to also provide on that point. Now, question number 46. Alkanoids are naturally found in what? Don't forget that alkanoids are esters. Okay, that's another name they are called. They undergo the process called esterification. Reaction between alkanol and alkanoic acid, okay, gives us alkanoids and water, okay, or ester, through the process of esterification. So esters usually they have a property which is a sweet smell. Okay, that's why they use them in making of yogurts, or making of ice creams, because of the sweet smell that they have. If you are manufacturing them, you can begin to perceive the fragrance they have. So alkanoids usually are naturally found in what? Lipids. We are lipids. When we talk about lipids, lipids are your fats and oil, fatty acids. We have vitamins, we have proteins, we have rubbers. So esters usually, okay, are from fats and oil. Okay, so and we say the fats and oil are from animals and then also from plants. That's how we get what lipids are. Okay, and that is I mean the lipids are actually the building blocks, okay, for fats and oil. Okay, building block for fats and oil. That's when fatty acids, okay, are eventually broken down, so we have them as lipids. So alkanoids are naturally found in lipids, okay, because that's where we got our fat and oil or the fatty acids from. Not vitamins, not proteins, not rubbers. We get them from lipids. So option A is the correct answer. Question 47. CH3, CH2, OH, and CH3O and CH3. Can we identify what they are? This is 1, 2. That's 2 carbon. Okay, then we have OH. This is an alkanol. 1, 2. That is your F. Okay, so that is ethanol. That is what this is. And then this is CH3O CH3. Okay, of course, this is your ether. Okay, because of this. Okay, this is methyl ether. Okay, dimethyl ether. We have 2 dimethyl here. Okay, ether. So we have, this is ether. This is alkanol. Alkanol, ether. One of the questions we solved earlier on, we are used this as an example to check if they have functional group isomers. Okay, so that was it. So if you have seen that, it is so the relationship between the 2 compounds above is that they are what? Are they allotropes? They are not allotropes. Allotropes are different forms in which atoms of elements can exist in their physical state. Okay, so this one are not atoms of the same element, so they are not allotropes. So we eliminate this option. Isotopes, isomers. Please don't get confused. Isotopes, isomers. Isotopes is a phenomenon where 2 or more elements, okay, actually have the same mass, the same atomic number, but different mass number. So we are not talking about mass number. We are not talking about atomic number here. So this is eliminated. Isomers. Isomers are when we have 2 or more compounds actually having the same molecular formula but different structural formula. So which means that if you count the number of carbons for the 2 of them, are they the same? If you count the number of hydrogen for the 2 of them, are they the same? If you count the number of other elements like oxygen that we have here, are they the same? So if they are the same, but when you draw them in the space, spatially, structurally, they will be different. But when you look at the numbers of atoms that make up that compound, they are actually the same. Let's see. We have carbon 1, 2, 2 carbon here, C2, H is We have 3 plus 2, that's 5, plus 1, that's 6. Then we have O here. Then we have, how many carbons do we have for this? We have 2 carbons. How many hydrogen? 3 plus 3, that is 6. And then we have oxygen. So you can see that they have the same atoms that combine together to form those elements. So both of them have the same functional group isomer. So they have the same functional group. So they are what? Isomers. So which means that option C is correct. Isobar, that has to do with the pressure, okay, that they have there. So the correct answer here is option C, isomers. Now let's move on to question number 48. The composition of alloy permalloy is iron and what? So there are 2 elements that actually make up this permalloy. Now permalloy is a type of magnet, okay, that is used in when you see some electrical gadgets that we have, you have them, those magnets, they have them inside of them, okay. They are made from alloy of iron, okay. That's why we call them permalloy, okay. They are made from that. It usually consists of about 20% of iron, okay, but a larger percentage of that contain that iron, that alloy, is actually what? Is nickel. Nickel has about 80% of nickel in this, and then 20% of iron in it. So which means that we have 20%, and don't forget that alloy has to do with what? 2 or more metals, okay, or elements that are combined together to form a desired or desirable, you know, traits that we actually want to find. So we have the composition of alloy. Permalloy is iron, and what we already said, it contains, permalloy contains 20% of iron and then 80% of nickel. So option A says copper, option B says nickel, option D says lead, and then magnesium. So the correct answer here is option B, nickel. Now question number 49. Aqueous solution of sodium hydroxide can be used to test for the presence of what? Roman figure 1, we have calcium ion. Roman figure 2, we have zinc ion. We have Roman figure 3, copper ion. Actually, sodium hydroxide is used to test for the presence of most metals, okay. If you put them, if you react these metals, maybe the salts that contain any of these metals, okay, react to sodium hydroxide, there will be reaction. Now for calcium ion, if you react it with sodium hydroxide in drops first, remember in your qualitative analysis, okay, where we talk about identification of ions, okay, your anion and cation in your practical chemistry, okay, usually we'll talk about the test, we'll talk about the observation, and then we'll talk about your inference that you're drawing. So for the test, if you react calcium salt, a salt that is unknown but it has calcium in it, okay, react it with sodium hydroxide in drops first to see if there's going to be any change. Yes, once you drop it, we are going to have a white precipitate will be formed first, okay, then continue adding, okay, add in excess of that sodium hydroxide. What happens? The color remains unchanged, the white precipitate remains there, okay, for sodium, for calcium salt, okay. Now for zinc salt, the same thing happens. React to sodium hydroxide in drops first. What happens? White precipitate will be formed, okay, but on continuous addition, when you add in excess of that sodium hydroxide, what happens? The color eventually disappears, so the white precipitate becomes colorless, okay, in case of zinc. So the same thing happens for copper. Copper is different because copper has a blue color. So when you add sodium hydroxide into it, a blue, you know, precipitate, a blue, solution will be formed. This does not form a white precipitate, it forms a blue precipitate. So the question says that aqueous solution of sodium hydroxide can be used to test for the presence of this. So you can use it to test for calcium ion because the white precipitate will eventually what will be formed. In addition to it remains the same, so you know that, oh, it is actually calcium ion. If you react a salt unknown that has zinc in it, how do you know that it is zinc ion that is there? When you react sodium hydroxide, what happens? You have a white precipitate first in drops as you drop the sodium hydroxide, and then when you add more in excess, what happens? It becomes colorless. Oh, you say, oh, that is actually having a zinc ion present in it. And then if it is the salt that has copper present in it, what happens? By the time you add sodium hydroxide in drops first, what happens? You are going to have a blue. Add excess, you still have the blue coloration. So which means that option A says I only. Is it only calcium ion? No. Option B says I and I. So calcium ion and copper ion, that is no, because this is also involved. Option C says I and I. That's calcium ion, zinc ion, copper ion. This is correct. Option D says I and II only. Calcium and this, that is no. So aqueous solution of sodium hydroxide can be used to test for the presence of calcium ion, presence of zinc ion, and presence of copper ion. So the correct answer is option C. Now question number 50. This is CH3, CH3, CH3. We have a carbon at the central atom here, and then we have OH here. Okay, CH3, CH3, CH3. Then we have OH here. So you can tell what kind of alcohol is it, because this is what? This is OH here. This is what? A tertiary alcohol. Why? Because the carbon that is bearing, that is attached to the hydroxyl group, OH group, is actually bearing about 3 different what? Methyl group attached to it. So this is a what? A tertiary alcohol. But the question says the IUPAC nomenclature of the compound above is what? If you take it this way, longest chain we have 1, 2. Okay, 1, 2, and then OH. That's not the longest we have. We can take it this way, 1, 2, 3. Okay, this longest chain, you can take it like this way, 1, 2, 3. You can take it this way, 1, 2, 3. So the longest chain is actually 3. So let's take it this way, carbon 1, carbon 2, carbon 3. What name is that? What parent name is that for the alkane? That is propanol. Okay, that's propane. Okay, but because we have, this is OH group, so this is supposed to be propanol, but we have, this will now serve as a substituent group. Okay, so this is serving as, that's the methyl group. Now it's going to be as a functional group that is acting as a substituent. So we have a methyl group on carbon 2. This is carbon 1, carbon 2, carbon 3. Don't forget the parent name is actually what? Is propanol. This would have been propanol, but the OH is actually on carbon 2. Okay, so that will be propan2ol. The OH is on carbon 2, so it will not just be propanol, it will be propan2ol. And then this one is acting now as the what? As the substituent on, still on carbon 2. So we'll say that will be 2. This is the methyl group, methyl propan2ol, 2-methyl propan2ol. So that is the IUPAC name. We have option A says propan1ol, no, butan1ol, 2-methyl propan1ol. The OH is not on carbon 1, so it cannot be 1ol. So it is 2-methyl propan2ol, 2-methyl propan2ol. So the correct answer is option D, 2-methyl propan2ol. I hope you enjoyed this content, because I really did. If you have done that, please do well to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we update or upload our next video.